Right, question 17 and 18 are both core practicals, okay? You really need to know your core practicals as well. Yeah, the method, you obviously need to know the main parts of the method, but the analysis, how, what you did with the data to find your values is crucial. Right, what have we got? 17 is the measuring G practical. Now, we've all done this. We've all done this in class, or we've done it at home, or we certainly watch videos, and you should know the different ways of measuring G, because I think we looked at about 2 or 3 different methods. Right. Well, with this method, we've got a timer, and it drops to a height h. So we've got the distance it falls through and the time it takes. Now, if a couple of you went down the route of measuring the final velocity, we don't need to do that. Not in this method. Okay. A few of you said, okay, we can calculate the average speed and then double it. Yeah, you can do that, but that is a bit of a convoluted way of doing it. There's a much simpler way, which is using the equation S equals UT plus a half AT squared. Now it drops from rest, so this becomes, okay, H equals a half G T squared. Okay. Now, in the practical, in this experiment, what we do is we vary H and we measure T. So H and T become variables. It even tells us that. Okay. This was repeated for decreasing values of L. Right. So what do we plot? Because there's a graphical method to find G. Well, we plot. That's in the form y equals mx plus c. So we plot that on the y-axis. We plot t squared on the x-axis, which means the gradient is a half g. So we need to show on the axis. That should be, so if we plot h on the y, not t, but t squared on the x, it's a straight line through the origin, and we measure the gradient and that's equal to a half g. Okay, that's what you needed to explain in that question there. Right, question 18. Similar deal. It wants us to explain how we use the measurements to find resistivity. Okay, but first, it talks about the method a little bit here. State the physical quantities we should measure, or she should measure, suggesting a suitable instrument for each. Now, what have we got? Right, well, if we want resistivity, okay, remember, resistance is directly proportional to L, inversely proportional to A. The constant of proportionality is that. So if we want rho, we need to measure R, L, and A, don't we? So there's 3 things we need to measure. Now, well, there's 3 things, there's 3 quantities we need. Okay, right, the easy one. We're going to measure the resistance of this section with an ohm meter. You could say multimeter, set to measure resistance. You could even say, well, I'm going to use a voltmeter and an ammeter, but the diagram there shows an ohm meter. So we're going to measure resistance of each section, of that section with an ohm meter. We're going to measure the length of this section with, again, it's given there, meter ruler. Okay, right, area. We do not measure cross-sectional area. What do we measure? We measure the diameter. If you have, I'll just do a close-up here. If you have a section of wire, you actually measure the diameter, don't you? Now, what do we use to measure it? Micrometer, okay, or vernier calipers. I'll allow that. Okay, but a micrometer gives you one extra degree of resolution. Now, the micrometer is measured to the nearest 100th of a millimeter. Okay, so they're the quantities we measure. Describe how you use the measurements to find rho. using, now this is the important bit, using a graphical method. Okay. Previous question gave you axes, but there's nothing to stop you going, okay, what am I going to plot here? Well, let's figure out first. Well, we've got, like I said, resistance equals rho L over A. Just going to do a slightly different version. Resistance equals rho over A times L. Why have I done that? Because it's more obvious that R goes on the y-axis, L goes on the x-axis. The gradient is M. So if we have increasing values of L, that would give us increasing values of R, and the constant of proportionality is rho over A. Okay. One last thing, I think you should see for the mark scheme, it wanted you to explain how you got your values of A from your values of D. Okay, well, A is pi R squared, or A is pi D over 2 squared. Okay, so that is how you do that one. Okay. Next question. Question 19. This was tricky. It is tricky, this. We all know the efficiency equation. It's useful energy out over total energy in. Okay? Or useful work out over total work in. Now, the trick here, or the difficult part, is figuring out what's the useful energy we get out, what's the total energy we put in. Okay, well, it says this machine is designed to lift this thing up the slope by making this thing move down. So when the 8 kilogram mass moves down, it loses GPE. Okay, so that's the energy in. The total energy in is the 8 kilogram mass losing GPE. Now the useful energy out is the 50 kilogram mass gaining GPE. That's the key important bit there. Okay? Right. How do we calculate these values? How do we calculate the loss in GPE? Right. So this is fairly straightforward. Let's go from the top to the bottom. So the 8 kilogram mass is going to go from the top down to here. So for the 8 kilogram mass, the change in GPE is mg delta H, which is 8 times 9.81 times delta H is 2. Okay. That is 16 times 9.81. Doesn't matter. Right, the 16 kilogram. Right. The change in gravitational potentiality. Right, again, it's mg delta H. What's the delta H here? This is the trickiest part of the question. Right? Now, when the 8 kilogram mass goes down by 2 meters, what height does the 50 kilogram mass go up? Right? Now, it does not go up 2 meters. It does not go vertically up 2 meters. It moves up the slope 2 meters. Okay? So, when this fella goes down through 2 meters, this fella will move up the slope through 2 meters. There's the key part there. Right. We need to know this angle, don't we? That would be really useful because we need to resolve at some point. Right, what's that angle there? That angle there, okay. Now it's a right angle triangle, so that angle there, let's call it theta. Sine theta is opposite over hypotenuse. Opposite over hypotenuse. The opposite in this case is 2 meters. the hypotenuse is 15. So sine theta is 2 over 15. Theta, that angle, the angle of incline is 7.66 degrees. Okay, so that's going to come in useful. Right, when the 50 kilogram mass moves 2 meters up the slope at an angle of 7.66, we need to work out the vertical height it moves vertically upwards. Okay? Now that's going to be the vertical component of the displacement up the slope, isn't it? Okay? Now, that vertical component of displacement, okay, is a sine 7.66, isn't it? The horizontal component will be the cos, because that's adjacent to the angle. So this one is, right, so it's good. The hypotenuse is 2 meters, because it's only moving 2 meters up the slope. So 2 times sine 7.66. Now sine 7.66 is 2 over 15, isn't it? Okay. So the vertical displacement is 2 times 2 over 15. Okay. So going back to here, we've got 50 grams going up times 9.81 times 2 over 15 times 2 is 4 over 15, which is, I've written it down, 0.267, I think. I'm going to check that. 2 divided by 15 equals times 2, 0.267, yes. So, when the 8 kilogram mass moves down through 2 meters, the 50 kilogram mass will move upwards through a height of 0.267 meters. Okay, right. Efficiency now. So it's useful out over total in. This is the useful out. This is the total in. So we just divide them. Now, neatly, the 9.81s will cancel. So the efficiency becomes, okay, start again. I will start again. Efficiency is the useful out, which is 50 times 0.267 over the total in, which is 8 times 2. Now that comes out as 0.83, which is 83%. Okay, so there you have it. You've just writing down that value, okay, shows that the efficiency is actually less than 90. There you have it. Question 19, almost there.